Hi everybody! Today we're going to explore a fundamental result in quantum mechanics, the Heisenberg uncertainty principle. The uncertainty principle tells us that it's impossible to simultaneously measure the position and momentum of an object with unlimited precision. The product of their uncertainties has a fundamental lower bound of h bar over 2. So the more precisely I know an object's position, the less precisely I know its momentum, and vice versa. Note that this bound has nothing to do with inaccurate or flawed measurement techniques, but instead comes from the wave properties inherent to the quantum mechanical nature of the world. So note that the right-hand side of this formula is really, really small. H bar is on the order of 10 to the minus 34 joule seconds. So the product of these uncertainties only becomes significant for really small objects. But all objects, all matter has wave properties, from electrons to baseballs. So even though we're used to thinking of a baseball as a particle-like object, the uncertainty principle still applies to measurements of its position and momentum. Let's see how this works in a problem. An astronaut on a spacewalk throws a 140-gram baseball straight away from her along the x-axis through the vacuum of space. An onboard sensor can measure the position of the thrown ball with a precision of 0.3 millimeters in each direction. What is the minimum amount of time it would take the ball to move 1 centimeter in the y direction due to the uncertainty principle? What would this time be for an electron? So what does it mean to throw a baseball exactly along the x-axis? It means that we'd like the baseball's position to be at y equals 0, but because my measurement device only has a precision of 0.3 millimeters, I can't tell the difference between y equals 0 and y equals 0.3 millimeters. So there is an uncertainty in my measurement of the y's position of the ball. So delta y equals 0.3 millimeters. And because of this uncertainty, there is an inherent uncertainty in the measurement of the ball's y component of momentum due to the uncertainty principle. So applying the uncertainty principle to the y direction gives delta py, delta y, greater than or equal to h bar over 2. So using the fact that a thrown baseball has a non-relativistic momentum, we just plug in momentum equals mass times velocity. And we can solve for the spread in the ball's y component of velocity due to this uncertainty in its y location as it's thrown. And that result will give us a spread delta Vy greater than or equal to h bar over 2m delta y. We're plugging in the mass of the baseball here. So this is the minimum spread in the ball's y component of its velocity as it's thrown. If the ball moves at the top speed of this spread, then we could plug in the numbers for the equality on this right-hand side, and we would find Vy equals 1.25 times 10 to the minus 30 meters per second. Now, classically, we'd expect to measure 0. However, quantum mechanically, due to this uncertainty principle, we can measure a tiny, tiny, tiny velocity in the y direction. And it's so small precisely because the mass of the baseball in the denominator of this equation is so much larger than h bar in the numerator. So if the ball has this velocity, it would take a time of the distance we want to measure it having traveled in the y direction, which is 1 centimeter, over this velocity, which turns out to be a time of 2.54 times 10 to the 20 years to see the baseball move just 1 centimeter off of its classical trajectory due to the uncertainty principle. Given that scientists measure the age of the universe as 13.8 billion years, this result says it would take 10 billion times the age of the universe to see the ball move 1 centimeter off of its classical trajectory due to the uncertainty principle. Let's contrast this with the situation for an electron. So here we computed this time for a baseball. Let's plug in the electron's mass to this formula here, which we gave here. And we would find a time of 0.05 seconds. What this says is that if I shoot an electron in the x direction, but can only measure its y location with up to a precision of 0.3 millimeters, then it would take a very, very short time, 0.05 seconds, to measure the electron to have moved 1 centimeter in the y direction. So this is the basic idea behind why we can't think of electron orbitals in the atom as classical orbits. An electron's position is inherently fuzzy due to the uncertainty principle.